What I'd like to do today is to tell you about some of the studies we've been doing on tool use and cognition in corvids, such as the rook pictured here, and the jays and jackdaws and magpies that David mentioned, and also in young children. Now, the studies really began in the 1990s when colleagues, and in particular Gavin Hunt and Russell Gray, discovered that one species of corvid, the new Caledonian Crow, not only uses tools but actually makes them. And outside of the humans and the non-human great apes, this was the first animal example in a very distantly related species that actually manufactures tools. And I'll play you a little video of a crow in action. Now, when this work was first discovered, it took them a long time to see the crows actually doing it. In fact, it was seeing the little imprints, the little doily patterns, where the crows had secretly been at work, that led Gavin Hunt, who's a remarkable field biologist, to make these discoveries. And it was a number of years later that he actually saw them doing it. And here's one example here of a tool made from a pandanus leaf. And one of the interesting things about these New Caledonian crows is that in different parts of New Caledonia, they make different kinds of tools. So in some areas, they make thin ones. In other areas, they make fat ones. And in some areas, they make ones that have little step ridges on them, so sort of look a bit like that. And some of them, it's just 2 steps, or some of them, it's 4 or 5 steps. And they also fashion hooks, as you can see in the artist's depiction on the left, where they can fashion a hook from the stick, which they use to get grubs out of crevices. And one of the interesting things that the artist is depicted here is that these grubs, or these bugs, are actually out of view, and so the bird is having to, at very least, have some sort of object permanence to know that it's got to get this tool, to use this tool in a way to get this grub that is otherwise out of sight. And what they do is not to sort of jab or to stab, but they actually sort of irritate the bug, and that irritation causes the bug to bite onto the end, and then whoosh, out the crow pulls it out. And they're not very good at this when they're babies. It takes them quite a while to acquire the fine motor skills to do this behaviour. Now, the next bit in the puzzle actually didn't happen until 2009, when we discovered in my laboratory in Cambridge that there are other crows, ones that in all the literature it says they don't use tools at all, who will nonetheless readily do so in the lab when given a problem-solving task in which they can't otherwise get food. And the first bird to show us this information was the rook. And here you can see a depiction, actually. This is from my husband Nathan Emery's new book, Bird Brain and Exploration of Avian Intelligence. And he's talking about the complexity of some of the tool use that is used by both the rooks and the New Caledonian crows. And in this particular example, and if anybody's interested, I have actually got a video of a bird doing this, but in the interest of wanting to stick to time, I'm not going to show it now. But this is actually an 8-stage task in which the bird goes and uses one tool to get a second tool, and a third tool, and a fourth tool, and so on and so forth, until finally, having got the 7th tool, that tool can be used to retrieve the food. And this particular New Caledonian crow, who was very, very good looking and very sort of dark and handsome, we called 007 because he reminded me of Sean Connery in Sean Connery's heyday and James Bond. And I filmed this working with Chris Packham because we made a 3-episode series called Inside the Animal Mind. It was originally for BBC Two Scotland, but then Nova put money in, so it's come to the States, and it's now actually gone internationally around, so that's one of the clips. But the rooks in the wild don't use tools, and we think that's because they have very long beaks, and the kinds of foods they use don't require a tool. They're digging in the earth in order to get mealworms or potatoes or earthworms or those sorts of things. And so they have bits, you'll notice in the video when I play it in a minute, they have little bare faces around the edge of their bill, which we think is an adaptation actually, because they're often getting dirty in the mud and it helps to keep that part of the bill nice and clean. But what we found in captivity is that they spontaneously use and make tools. Now, one of the most famous examples of tool manufacture in the lab came from Betty the New Caledonian Crow, who was found to take a piece of straight wire and bend it into a hook in order to retrieve a bucket of food that was out of beak reach. And here's one of our rooks doing the same thing. This is Sylvie Guillaume. Now, you might think of Sylvie Guillaume as a famous ballerina, which is true, but this Sylvie Guillaume is a famous rook. And here you see her taking a piece of straight wire, and she's using the tube to bend it. She's now bent it, but obviously it's the wrong way up. She now flips it the correct way up so that hook's in the bottom. And then she uses it to get the food. So this was the beginning of our experiments. And we were quite surprised at just how good the rooks are at these tasks. In fact, here is a comparison of the habitual tool-using New Caledonian crows with a pandanus leaf in its bill and the barefaced rooks, for which there's no evidence of tool use in the wild. And we find that our rooks, just like our New Caledonian crows, are using multiple tools, so they can use one tool to get a second tool, to get a third tool, and so on. They are able to make the right choices in terms of what kind of tool you need, in terms of how long it is or how big it is. They are capable of modifying tools, so if there's a stick and it's got too many prongs in the wrong places, they know which ones to pull off to make it work. They're capable of sequential tool task, where you might have to take one tool to get a completely different type of tool in order to get the food. And they're also past the Aesop's fable water task, which I'm going to come on to and explain properly in a minute. And finally, hook tools. So what is the Aesop's fable task? Well, it was inspired by a fable called The Crow and the Pitcher. And in the fable, the crow is thirsty and uses stones to raise the water level in order for it to be able to have a drink. Now, in the UK, where I'm from, the procedures for animals are very, very strict, and there is no way that the Home Office would be happy about making our crows thirsty. So instead, we bribe them. And the most effective bribe for a corvid, and I've known many different species of corvids, and I haven't discovered a single one that doesn't fall for this bribe every time, is waxworms, or wax moth larvae, I should say as a proper biologist, but everybody calls them worms. And these are the Belgian truffles of the corvid world. They absolutely go ballistic for these things. So if you want to bribe a jay or a crow to do something, you just have to float one of those near, and instantly it's like, right, what do I need to do? So that's what we do. We float a worm on top of the water. And here you're going to see a little bit of footage. This is one of our Eurasian jays. He's called Romero. And there he is, dropping stones to raise the water level in order to get the worm. And that's one of those waxworms, wax moth larvae that the birds love. Now, because this is such a simple task, the advantage of it is that it's very easy to make specific manipulations, and actually using an interventionist approach, we can start to ask questions about how are they solving the task? To what extent might cognitive processes, as opposed to trial and error learning, be responsible for their performance on these tasks? And I don't see these as either or. Very often I think you'll see a combination of the two. You'll see basic associative trial and error processes interacting with cognitive processes. Now, the one example that I want to give you in the remainder of my talk is a choice of objects. So in truth, we know that if we give them a choice of substrates, so you have a tube with water, a tube filled with air, a tube filled with sand, so you've got liquid, gas, solid, they only put stones into the one with liquid. We also know that it's goal directed, so if there are no worms floating on top of the tube, the worms are somewhere else, then they don't drop stones into the tube. But the one I want to focus on now is object choice. And what you're going to see in the next experiment is we give our birds a choice of two types of objects that they can put into the tube. And one floats and one sinks. And obviously, if you put ones that sink into the tube, the water level will rapidly rise and the bird will get the worm. If you put ones that float, the water level won't rise, and very often if you put enough of the ones that just float in, you won't be able to get the worm at all because it'll just get buried under the ones that float. So here's an example of this. So here we've got marble ones that sink, and we've got cork ones that float. And this is Romero's first trial. Tries one of each. Removes the offending item. And then collects his worms. This is what the data looked like. So what we actually do is look at the order in which the items are inserted, so they get 10 in any one trial. And in the real experiments, as opposed to the pretty BBC television footage, we have rubber ones and foam ones, and the rubber ones are dense enough to sink. So you can see that the more green means the more they're getting it correct. And you can see that they rapidly learn to be selective for the rubber ones. And this is what the overall results look like. Obviously, if you were to put half and half, that would be chance level. And you can see that both Hoy and Romero are significantly above chance in this experiment. So we then did a similar thing for children. Now, obviously, we would have had great difficulty getting ethical approval if we wanted to float food on the top. And I'm sure that the children, or most of the children anyway, wouldn't have been very keen on retrieving worms. So instead, we use little stickers. And these tiny stickers that float, which can then be exchanged for a very special sticker that you can't get anywhere else. It says University of Cambridge, Comparative Cognition Lab, I'm as clever as a crow. And the children love these stickers. So this is what the basic task looks like. And there she looks rather pleased with herself. Now, in these experiments, we're not really interested in the performance on this basic task. We're using this really just to go on to the next stage, which is to ask questions about what they understand, which is why I'm going to focus on the hidden and floating experiment. And here you'll see an example of a 6-year-old. I think you can see he hasn't got all the details quite down yet. And he doesn't look too happy about it, does he, bless? Now this is a 9-year-old child who has got the details down. There you go. And this is what the real results look like. We tested children of age 4 to 10. And you see that 4 and 5-year-olds are at chance. 6 and 7-year-olds are a little bit better, but they're still not very good at all. It's not until they're 8 years of age that they're able to solve this task statistically. And that was very surprising to us, because a lot of other cognitive abilities tend to develop sort of gradually, but over the sort of age 3 to 6 window. So we were really surprised that it's not until 8 that these children are figuring out this task. And we wondered what the problems might be. And of course there's many possibilities, and one of them is that we may in fact see cultural differences. It would be very interesting to look in cultures where tools and having to make things and be very physical in the world is critically important to them. I mean, I know myself, in these days of a smartphone, I have no idea physically how it works. I just know which buttons to press in order to do the basics, like answer a phone call and take a photograph. And if anything gets more complex than that, I just go into the Apple store and say, can you help me? So I don't really make much effort to understand the physicality, and we wonder whether culturally that could be a component. But what I want to do in the final experiment is share with you our very latest research. It's not published yet, we're just starting to write it up now, trying to look at what it might be that's causing the children to have such a late development with this. So this is brand new research that we're just writing up at the moment. And what we're doing here is we're manipulating functionality and reward history. So now there are going to be some objects that sync, so they're functional, and there'll be some objects that float, so they're not functional. But sometimes the children will get rewarded, so they'll get the sticker at the end, and sometimes they won't. So this is how the design of the experiment works. We've got one case where the functional object does get you the reward, the sticker. There's another case where the functional object doesn't get you the reward because the nasty human experimenters have done something to the tube, which means that they're not going to get the reward even though it's sunk. I'll show you the examples in a minute. There's the one where the non-functional object does get you the reward, so even though you chose the right one, the experimenters craftily manipulated something so you still get the reward. And then there's the fourth case where it's not functional and you don't get the reward. So there's basically in the non-functional ones, the F minus, it's either because it's hollow or floating, and in the F plus they sync because it's functional, but in one case you don't get the reward. So the idea behind it is that there are 2 phases to the experiment. In the first phase, there's a tube, and the children get experience of putting these objects in and seeing whether or not they're functional and whether or not they get the reward. And then in the second time, they get the choice of tools. They'll get 5 of one kind and 5 of another kind. It's always 2 types of tools that they can choose between, and it's a different apparatus, but it works on the same principle. So in the non-functional but rewarded one, these objects float. That's why they're non-functional. But you can see that because of the way the tube works, the water level is nonetheless coming up. And here's an example of a child doing this.
And 1, 2, 3, go! Did you get the token?
Yeah.
Why?
Because they kept, because you turned it and then it went down, and then the red things moved.
Okay. Why don't you choose a sticker?
So there you go. that's an example of the non-functional but rewarded. This is the other version. This is the one where it's functional. In other words, they sink, but it's non-rewarded because water's flowing out the side. Okay, so that's the way we've designed these tests. And therefore, the water level constantly goes down, not up, despite the fact that they're putting these sinking ones that should be displacing the water. And that's what this looks like.
I'm going to give you these and this, and you have 1 minute to get the token. So do you think you can get the token?
Nah.
Why not?
Because there wasn't any more.
There wasn't any more what?
There wasn't any more of the blue thing.
All right.
So there you go. And then, in terms of the anatomy of the choice, in the second phase, they're given two types of objects. So, for example, perhaps the most interesting case really is where we pitch one that isn't functional but is rewarded, the red ones, against the one that is functional but isn't rewarded, the blue ones. We give them a different apparatus, you'll see a video in a moment, but with the same principle, with the water that level needs to rise if they're to get the sticker. And the child is told there are 10 of them, there are 5 blue and 5 red in this example. It's always a 2-object choice, and the child selects 5 of them. So, for example, if she were to choose these, then that would indicate she'd chosen 2 of the red ones and 3 of the blue ones.
Do you think you can fish it out?
No.
Alright, so I'm going to give you this little tray here. And I'm going to give you these 10 objects that you played with before. Do you remember them? Yeah? I want you to choose 5 objects that you want to use to get the token out. The 5 objects you want to use to get the token out, I want you to put them in the little tray over here. Okay? Which 5 would you like to get the token out? Put them in the tray. Alright.
So that's an example of her choosing. And it's the pattern of these choices that tells us something about their decision-making processes, about whether it's specifically being guided by functionality or whether it's been previously rewarded or not, or a combination of the two. And the results we have are quite striking. This is the percentage of children in each age group that chose 95% or more of the expected objects for each strategy. And you can see that reward history is pretty flat. It's pretty much at 0. So children don't seem to rely on their experience of being rewarded to drive their choices. So they're not using previous reinforcement history. It doesn't look like this is an associative account. It looks like initially they're really bad, which probably explains their poor performance, but then suddenly at age 8 things change. And from age 8, function-based strategies are significantly better at predicting behaviour than reward-based strategies. So as the children get older, functionality increasingly becomes the only factor that they seem to be taking account of in their selection of tools. I'm sure you can guess what the next step is. We'd now really like to test the crows and see whether our new Caledonian crows and that habitually use tools in the wild and our non-tool using rooks and jays that are very happy to use tools in the lab, whether their decisions are also based on functionality, or whether, as the existing literature hints at, it's in fact more likely to be based on reinforcement history or reward history.